Okay, so what I'm going to do today is you're going through the 2D numerical solution. You've done an example, I think, in discussion. Let me just flip something here. So I'm going to cheat a little bit. I'm going to give you the filled out notes for the remaining slides for the 2D for two reasons. One, I need to get through the 0D transient stuff today. Two, this is extremely tedious to write. So what I've done is taken the 4 slides that I didn't yet write out, and I've uploaded them to the lecture folder on Canvas, so you can find this there, right? So I'm going to go through it really quickly, just cover the highlights, and then we'll move on to the actual stuff that I want to get to today. Okay, so remember last time we were talking about this 2D numerical solution. What we're trying to do is come up with energy balances around these control volumes. For 2D, we have internal nodes, we have the 4 boundaries, and we have the 4 corners. So you should have 9 different control volumes or nodes that you're doing an analysis on. Again, it's a little tedious, but the cool thing is you go through this pain, and in the end, you have this really cool solution, like this solution that it's really powerful. You can do all kinds of stuff with it. And it's just a very flexible approach. So this is the 2D solution for the internal nodes. Where we left it last time was I went through this example of what it would look like with a constant conductivity. This is the formulation if the conductivity is a single value. So I think I basically wrote this out last time. What we can then do is go back and look at how the formulation would change now that we're going to want to account for the fact that conductivity is changing as a function of position x. Right, so we had previously said k, let's see this guy, can I do this? Ki, right, that's the conductivity of the ith node or the node in the ith node in the x direction. And that's constant as a function of y. But you can see like this would be a constant for every single case. So it doesn't have to account for the fact that there's potential differences. Now if we go to the next, so this is a revised energy balance for our composite problem. So how does the solution change? Well, first of all, we need to account for the fact that conductivity might change node to node. It doesn't necessarily, but in this problem, there's a place where it does. So we have to look at the boundary between the 2 nodes and agree on a conductivity at that position. So for example, like here in this control volume up here, if I'm going to compute the heat flow from node I plus 1 to node I in this direction, it's going to have to agree exactly with when I create a control volume around this node, the heat flow in the other direction. Right? Those have to agree. They have to be the same value. So I have to evaluate anything like K at the boundary. Right? Anything like conductivity or area that's changing has to be evaluated at the boundary. So what you see here is this Q dot Rij is looking at the average properties between I and I plus 1. That's the conductivity at the boundary. Incidentally, if you're doing this for generation is just evaluated, because it's a volumetric thing, it's just evaluated at the node, not at the boundary, okay? So we go through and we do this for heat flow from the right for this boundary, heat flow from the left for this boundary. Since conductivity is not changing as a function of y, the top here and the bottom here, right, these equations here are the same. Those did not change from the previous formulation. So everything's the same, except now we're just accounting for the fact that conductivity here is this average value as opposed to the constant. All right, so then you can just go through, I guess I wrote these in terms of these dy, dx's. Really, these should be like, delta y or delta x, just to not be too confusing. But okay, so once you do that, then you have your energy balance for the node. And this is for the nodes, the internal nodes. I equals 2 to m minus 1, and j equals 2 to n minus 1. Questions on this slide? Okay. So what's left? We have to do the edges, and we have to do the corners. So this is, again, just showing you what's here. I would suggest, as you're going through your homework and maybe you're confused about how to set this up, just go back and look at these. They're on Canvas. So for the edge, what you want to pay attention to is the edges are basically the same, except now you have something coming in from the surroundings. So like up here, we have this Q dot top. Well, that's relating the surroundings to that node. So the driving temperature difference here from the top, instead of this being conduction, now it's convection for this problem. So we have convection coming in. We have the arrow drawn from the outer to sort of the external into the node. So that means it's external into the node, right? T out to the node index. So pay attention to that. And the other thing to pay attention to is the areas that are available for conduction here. These are like this area is now just delta y over 2, or dx over 2, or dy over 2, I'm sorry. dy over 2. So it's half the area. Like as opposed to the internal nodes, which has the entire dy or delta y, when you're on the surface, it's shrunk down. So the distance to conduct is always the same. It's always that delta x, but the area that's available for conduction is delta y over 2. All right, just bookkeeping on the areas, bookkeeping on the distances, and then looking at where the arrows are coming from, right? That's pretty much all this is. So you have to do this or repeat this process for all 4 surfaces. Questions on this one? Okay. Corner nodes, very similar, except now the areas both in the x and in the y are going to be half. Right? The distance to conduct is always the same, but the areas are half both in x and in y. Right? And so you're just applying the boundary conditions and kind of going through the analysis for each of these. So, I mean, yeah, there's not really that much more to say about it. Once you kind of get the hang of it for internal nodes or whatever, that's pretty much it. You just have to pay attention to the areas and the indexing. Okay? So, good. I'm sensing no questions on this. So let's go ahead and move on to the material for today. All right. Shifting gears a little bit, we've gone through now all of this steady state analysis. We are now going to dive into transient analysis. So the difference is in steady state, we're always assuming that there's been enough time that has elapsed where the system sort of reaches some equilibrium. And maybe that's, the temperature on one side and the temperature on the other side sort of settle into their values, and there's heat transfer occurring, but it's not really changing with time. Here now we're saying, let's allow this to change with time. Let's allow our problems to change with time. Let's add that time dimension to our formulation. How does this change our setup, our analysis, and kind of what does it add to the problem-solving requirements? So we're going to go through today like the simplest possible case for transient analysis. So we call this 0D transient analysis. We also call this 0D non-steady state. We call it lumped capacitance. Those kind of terms all are basically the same thing. But the main idea is we're going to find some body. That body is changing temperature with time, and we want to predict what the temperature change with time is analytically.